Welcome to my course Electrochemical Energy Storage, and this is module number 8, Advanced Materials and Technologies for Supercapacitors, and this is lecture number 36, where I will be describing the classification of the supercapacitors, which is of electric double layer capacitor type and pseudocapacitative type. So, in this particular lecture I will concentrate mostly on EDLC type, that is electric double layer type supercapacitors. So, the first is the classification of supercapacitors, then we will talk about the electrode materials for EDLC, electric double layer capacitor, which mostly includes activated carbon and also carbon nanotube and other carbonaceous materials. So, that will be introduced in this lecture, and then finally, we will describe the pseudocapacitative materials basic principle, and in the subsequent lecture we will talk more about pseudocapacitative materials. So, the supercapacitors, they are also termed, there are two terminology that is used for supercapacitors. One is ultra capacitors and sometimes they are called electrochemical capacitors as well. So, as compared to the traditional capacitor that you might be knowing, two metal plate and a dielectric there inside. So, the capacitance of the traditional capacitor, whatever is that, as compared to that, this supercapacitors or ultra capacitors, they have several orders of magnitude higher capacitance, and that is basically due to the fact that in case of these supercapacitors, high surface area is used. Initially, I introduced the supercapacitor in a gist form in my first module lecture, and lecture number 3 we talked about supercapacitors. So, there you have gotten the idea that what I mean by high surface area electrode materials and also thin electrolytic dielectrics. So, it is the charge separation at the surface of the electrode. So, the value of D is very small and value of the A, that is very large. So, they constitutes what we call this ultra capacitor. So, if you want to make a difference between these traditional capacitors and supercapacitors, in the latter form they do not have a solid dielectric, which usually we have seen in case of normal traditional capacitors. And there are two different types of charge storage mechanism. So, based on this charge principle of charge storage, we will differentiate between double layer capacitor, which store the charge electrostatically, and there is a second variety which is a bit difficult to understand. You will see that why I am saying that. That is known as pseudocapacitors, and in many instances they are somewhat similar to the battery type material. So, I will differentiate that. So, the capacitance value, this is very high, in the order of 1 to 100 farad you can get, and mostly they are used in car or bus or trains, where during braking, when they are in motion and then you apply a brake, that energy is used to charge this capacitor. And if you differentiate between battery and capacitor, you might be knowing that in case of battery, it requires some time, because diffusion is involved, some time to charge the battery. Supercapacitor charging is instantaneous. So, this regenerative braking that is used basically to charge this capacitor, and they are used when lot of current is required during its operation. For example, when the train or bus is accelerating, then you need lot of current. So, capacitive part gives that current, and when you break it, then it recharges back the capacitor. So, if you see a normal electric double layer type electrochemical capacitors or supercapacitors, they basically store the charge electrostatically. So, here are the example, there are two electrodes, and you know that during charging you will have to charge it. So, there is a surface charge in the electrode surface, only the surface phenomena is involved, and then you have electrolyte, and electrolyte has counter charges, and they basically adhered to this charge capacitor. One is positive, another one is negative. So, counter ions are different, and they are only present in the outermost surface of the conductive electrode. So, if you look at the electrode, you have a current collector, and then you have a electric double layer capacitor. So, this is charged only at its surface, and you have counter ions. If it is positively charged, you have counter ions which are basically solvated, and then you see that they are attached to the surface, and they constitute a double layer capacitor. So, you can find there is a electronic layer in the surface of the electrode, and there are ionic layers which is having opposite polarity than this surface charges, and that this opposite polarity ionic layer, they reside at the surface. So, if you look at it, and there are different models for how this supercapacitor actually store charge, and this is the latest one. So, it evolves over time. So, initially it was just the adherence of charge, but later people have described that there are two distinct layer that is formed, and the first one is internal Helmholtz layer, and this is just like a molecular dielectric, and mostly it is now understood that the solvated counter ion, you know that this is solvated. So, it is also polarized, and this is adhered to the surface of the electrode, and that forms this internal Helmholtz layer. And then of course, it depends on the chemical affinities of the ions to the electrode surface, and of course, the field strength that also decides this adhesion. And then you have an outer Helmholtz plane, and that refers to the distance. I mean, the distance is from the surface till the outer Helmholtz layer, and after that you can have a complete diffuse layer. So, I have shown only the negative solvated anions, negatively charged, but there are progressively positive charge as well. So, if you see the potential, so the charge is maximum here, and then inner surface layer, it is basically they get neutralized. So, the potential drop is there, and you can define this two different potential phi 1 and phi 2. So, phi 1 and phi 2 that basically decides the thickness of the so called outer Helmholtz plane, that layer, and then the potential is almost constant and this layer we define as a double layer. So, this L diff, that is defined as the double layer thickness. Now, if you consider an electrochemical double layer supercapacitor, so they usually have a structure that is similar to the battery. In battery also you have similar types of structure, two electrodes that is separated by a separator, and you need an electrolyte, and the ions and counter ions, they are there inside the electrolyte. So, in that way it is quite similar to the battery, but the performance wise it is different. So, here as you can see that when I try to charge this kind of EDLC, electric double layer capacitor, then ions and counter ions, depending on which one is your positive electrode, that is cathode, and which one is your negative electrode. So, accordingly you have this formation of this double layer, and this is eventually two capacitors which are connected in series. So, you know that when you connect it in series, then the total capacitance you can write using this formula, and the total capacitance you can evaluate from this particular formula. And if two same type of materials are used, then the C plus and C minus, they are similar. So, the total capacitor is basically decided by either positive or negative capacitance. So, you are losing the capacitance if you have symmetric kind of capacitor, EDLC type. So, if you want to differentiate the working principle of an EDLC and the batteries, it is quite straightforward. First, let us consider the charge storage mechanism, and in this case this is non-Faradic process, because there is no charge transfer, there is no change in the material's redox potential. So, valence state does not change unlike the battery material, and therefore, the charge is not transferred across the electrode and electrolyte interface. And in case of battery, you need finite time, so that the charge is diffused inside the electrode material. So, that is one distinction that one can make if I compare the double layer capacitor with the batteries. Now, if you consider the power density, it is certainly much higher, because it is just the adherence of the charge and detachment of the charge. So, it is a very fast process. So, the power density is quite high in case of EDLCs, typically 1 to 3 kilowatt per kilogram is a common power density, but in battery it is significantly low, because it is limited by the diffusion inside the electrode material. Particularly, you have seen in case of lithium ion battery or sodium ion battery, it needs a finite time to get diffuse inside or outside, inside or from the electrode materials. So, it is basically a slow process, but energy density is quite large, because of the fact that it is only at the surface that carries the charge. So, the energy density in battery is much higher, typically 50 to 200 watt hour per kg, but in case of the EDLC type of ultracapacitor, the energy density is very low as compared to this one. But since it is a very fast process, so the cyclability, if you consider it is quite long, 500 or more. So, easily you can go up to 1000 cycles without any loss of the capacity. But in case of battery, you have seen that this is a major problem, that progressively you lose capacity with charge discharge cycling. So, these are the common distinction between the ultracapacitor, which is EDLC type, and the normal battery, which we have already described part of this course. So, the performance of EDLC that is basically evaluated by the cyclic voltammetry. Already I have introduced the characterization tools, and also charge discharge characteristics, galvanostatic charge discharge, applying a constant current. You can do the galvanostatic charge discharge measurement, and also electrochemical impedance spectroscopy, that also give you a lot of idea about the performance of this electric double layer capacitor. So, you know Q, the charge store is C into V. So, I can write this equation for specific capacitance. So, that is dq by dV divided by m. M is the material active material weight. So, this is done, and then we do a little bit of jugglery, because dq by dt is I. So, I can always write that I divided by dV dt, and 1 by m stays there. So, that means this is nothing but dV dt is nothing but the scan rate of this CV. So, I can write this relation 1 by nu, that is the scan rate for doing the CV, and the mass involved is there. So, now if I want to have an idea about the total current that I get out of this process. So, I can write this relation that I, which is a function of V, of course, it changes with V. So, that is a function of V dV into the range of two known potentials. So, if I integrate from V 1 to V 2, so that is the two terminal voltage of this cyclic voltammetric curve, then I get this relation. So, C nu and m, that is dV, and this is from V 1 to V 2. So, this left hand side is nothing but the area under the curve. So, I is nothing but the current and this is the voltage. So, you know that that gives you the area under the curve, the total area. So, this is the hatched blue area. You can see this hatched blue line and it goes up to here. So, that is the total area that you are getting. So, this area I am terming as area number 1. So, if you integrate this, then you will get V 2 minus V 1 and this will come out because the capacitance of a material, the new value and aim that I consider constant. Now, if you go for the discharge, so this is the charge operation from here up to here. So, I got the total area which is the hatch, this portion, the blue portion, the total blue portion, and now I will do the discharge from here down to this voltage. So, from V 2 to V 1 I am discharging it. So, that area I can also estimate, which is the hatched area, see red line and this blue line. So, that also I can estimate, and using the same terminology, this I will get V 1 minus V 2 and this C capacitance, the scan rate, millivolt per millivolt per second, and the mass of the electrode material. So, eventually I am interested to know the area under this curve. So, I will have to subtract this whole area, which is area 1, and then this part, this hatched part. So, if I subtract this, I will get the area inside the CV loop. So, this also you can do that area 1 minus area 2, and that will give you area 3. So, you just put back the value whatever I have gotten for area 1 and area 2, and this yellow region you get this relation twice, this V 2 minus V 1, and this term will also there. So, eventually we get the area divided by 2 into the terminal voltage, that is the potential window, voltage window that I am using, into your scan rate and the active material. So, usually we use either the software which is associated with this galvanostat potentiostat system, which we usually use to measure the cyclic voltammetry. That software is used, or the current and voltage data that you can plot in a software like Origin or Excel, and then you can estimate this area from the curve that you have gotten. And then once you get that, then you basically you know what is the value of V 2 and V 1 and what is the scan rate that you have used to measure the CV, and you can actually estimate the specific capacitance. So, the specific capacitance, if you have a CV plot for a EDLC from a potentiostat galvanostat system. So, this is the procedure that is used to estimate it in farad per gram what is the specific capacitance of this capacitor. You can also use the charge discharge measurement, and this is this will certainly be a straight line because it is the adherence of the charge and coming out of the charge from the surface. So, it is a straight line, and this drop usually comes from the series resistance of the capacitor that already I have defined. So, you start from your open circuit potential and then go up to the maximum of the voltage window, and then there is a drop due to the value of internal resistance, and then you discharge it up till a voltage of this V 1. So, called V 1 is here. So, V 1 you discharge it. So, this time basically you are measuring. So, the capacitance you can calculate, this is quite straightforward. The value of Q by del V into M. So, it is coming just simple like Q equal to C V, this relation, and M is the active material weight. So, you get basically the specific capacitance which is measured by farad per gram, and 1 by M comes out, and this Q is again the relation is I, the current is dq by dt. So, the total charge is I into the difference in time. So, if I call it for the discharge, then the difference in time is T 2 minus T 1, and the voltage is from V 2 minus V 1. So, this relation, from this relation it is very straightforward to measure the specific capacitance. Once you have the specific capacitance, then you can go ahead and estimate the energy density. The dimension is whatever per kg. So, you know that this energy is half capacitance C by V square. So, this voltage window is V square max and V square mean. So, within that range you can put this voltage value. So, you can get the energy density, and power density, as already I have discussed in one of my earlier lectures, that is the energy density divided by the time that it takes. So, that will give you the power. So, power density also you can estimate. So, actually the capacitor is charged or discharged at constant current until the voltage between, if it is a 3 electrode system, so until the voltage between the working electrode and the reference electrode in a 3 electrode system, or the if you have a 2 electrode system where the counter electrode and the reference electrode is shorted. So, that is a 2 electrode system. So, that reaches the desired value. So, this voltage selection is based on you know the linear sweep voltammetry which I introduced. So, based on that you know what is the potential range that you will have to use for this kind of measurement. So, those are the characteristics that you want to measure in case of a electric double layer capacitor. The performance of the double layer capacitor that also can be estimated by a electrochemical impedance spectroscopy, and then I already described that how you can plot from the imaginary part of the impedance and the real part of the impedance, how you can plot the so called Nyquist plot. So, this is the typical Nyquist plot that you will be getting. So, as you can see that the value this R A that basically denotes the electrolyte resistance. So, that is the value of ESR. So, that estimate the not only the electrolyte, but the contact resistance, electrode, electrolyte and the contact resistance. So, that gives you this resistive value R A. Then R A B is the diameter, although sometimes it is suppressed, but eventually this is the diameter of this semicircle, and that usually gives you the charge transfer resistance. Already I have described that where from what is the physical significance of that. So, this diameter is the charge transfer resistance, and then you see that there is a line this BC. So, this kind of line that this red arrow, this shows that the change in the frequency while you do the measurement. So, progressively the frequency changes from here, because here you will not find the frequency, I am plotting only to impedance value. So, the frequency changes from lower frequency and up to the higher frequency. So, at medium frequency range, this resistance RBC, this line, that actually denotes the ion transport limitation in the electrolyte as well as in the porous electrode structure. So, porous electrode structure is not very significant in case of EDLC, because hardly the electrolyte goes in, sorry, that certainly goes inside the porous electrode, but there is no change in the valence state of the active material. So, that will also be there, this porous electrode structure, it will offer some kind of resistance and the transport of the ions through the electrolyte. So, that will contribute this BC, and this vertical line that is very characteristics of the EDLC material. So, that is a dominant capacitative behavior of the double layer formation at the electrode electrolyte interface. So, that is an indication that is a very fast process, and this basically this vertical line basically tells you that the formation of the EDLC. So, you can get this value to get the idea about the mechanistic point of view, what the idea how the EDLC type of material works. So, the first EDLC material which is basically used for various purpose is activated carbon, and activated carbon you can make by either physical activation. So, you take any carbonaceous precursor, that could be natural carbonaceous material like wood, coal or nutshell that you use. Then the first step is to pyrolyze this in an inert ambient. So, why you use inert ambient? Because you avoid the combustion of this carbonaceous material. So, oxygen is not there. So, it will not undertake any combustion, and all the heteroatoms that basically they are removed, and also the volatile matter they are removed, and it forms basically a char. So, this char is formed, and then there is a second step. So, in second step you do gasification. So, what you do that selective removal of most reactive carbon atoms, and you are using either steam, carbon dioxide. So, if you use that, then the temperature that is required for this gasification is around at higher range 750 to 900. If you use oxygen to remove this most reactive carbon atoms, and it is a controlled reaction. So, they are removed, and that actually gives the characteristic porosity. You need a porous material, so that the electrolyte can be going inside the electrode material to have a porous structure with high specific surface area, and that gives you lot of capacitance and as well as specific capacity. So, you need a porous material. So, this porosity is generated and you get this activated carbon. The second method that is used, we call this is a chemical activation. So, here also you take this carbonaceous precursor, and then you go for a impregnation step. So, you treat it with phosphoric acid or zinc chloride. So, they are called as activating agent, and this impregnation ratio that is this activating agent and the carbonaceous material. So, you can change that. So, that controls the not only the porosity, but the type of the porosity. So, usually it is kept between 0.5 to 5, and then after the impregnation you go for the thermal treatment, again at different temperatures depending on what type of this activating agents you are using. If you are using this H3PO4 or zinc chloride, then 400 to 600 degree Celsius, and progressively it goes high if you are using iron chloride, and sometimes you would use alkali material like potassium hydroxide or sodium hydroxide, then it is quite high temperature you need. And after the thermal treatment, this is washed, particularly when you are using sodium hydroxide for activation, then you need to wash the material that you have gotten, and that also lead you to the activated carbon. So, in case of this process, sometimes if want to do the activation with potassium hydroxide or sodium hydroxide, then it is found that this carbonization is necessary. So, this carbonaceous precursor that first you do heat treatment at inert ambient, typically 500 to 800 degrees Celsius to form the char, similar to the case that I have already described, and then you do the impregnation with potassium hydroxide or sodium hydroxide. Then you do the thermal treatment at relatively high temperature and wash this KOH and NOH, and you get this porous activated carbon. They are commercially available, different varieties are available from various vendors, and depending on the source that you are getting, that will control your specific capacity of the ultracapacitors. Apart from that, that thing is very common, but you can use a templated porous carbon. You can see that this is the template. You impregnate it with carbon precursor. And then you get rid of this template. So, these pores are very well defined, and depending on the template that you are using, you get a bigger pore. So, silica sphere that is sometimes used, which can easily be get rid of hydrofluoric acid treatment, and you get a very neat porous structure, and this is basically macropores of carbon. So, you can go for microporous material, which is zeolite is one of them, and then you load it with carbon, and then you get rid of this zeolite, which is aluminosilicate composition, get rid of that, and you get with silica gets off with this HF treatment, and you get a nice network porous structure for zeolite templated carbon, abbreviated as ZTC. So, you get this is your active material for EDLC. You can also use this. There are different types of pore diameters. So, macropore are quite large, then microporous is very small, and mesoporous is in between 2 to 50 nanometer, and this is around 2 nanometers, and macropores are in the order of microns. So, here you take again a template material, and then you go for precursor, which is carbonaceous precursor infiltration, and then you remove this template and you get this kind of porous structure. So, in activated carbon, the control of the pores that is difficult, and some pore could be tortuous. So, tortuous pore electrolyte diffusion will be hindered, but this kind of templated structure, you have a defined pore structure. So, certainly that will give you much better values as far as the specific capacity is concerned. Graphene is one material which has been proved they have very high specific surface area, and also they have good electrical conductivity and good capacitance. So, typically in graphene people have reported this capacitance is 550 farad per gram. So, graphene derived carbon which is having a specific surface area higher than this. So, it is about 3100 meter square per gram. So, people have used this microwave irradiation of graphene oxide, and then they are activated by alkali potassium hydroxide, and this type of material people have reported that they have a combination of micro and mesopore, and they provide a large accessible surface area for charge accommodation, and improved specific capacitance you will get both in organic as well as ionic liquid electrolyte. This electrolyte I will be covering in latter part of this module lectures. And most of these graphene derived carbons, they usually exhibited this electric double layer capacitance on one portion of the surface. So, as you know that the graphene is a stacked structure. So, they have limited ion diffusion path. So, if the channels are quite narrow, then electrolyte cannot be driven in that easily, because this track distance is pretty small. So, that is one disadvantage that people have reported. Carbon nanotube is another one. So, they have gotten quite good attention, and you can have either a spaghetti type of structure, noodle like structure. So, this carbon nanotube, they are good because their electrical property is conductivity is quite good, and they have good mechanical as well as thermal stability. So, one can use both single or multi-layer carbon nanotube, and typical surface area is relatively small as compared to your activated carbon. But due to this good electrical properties and mechanical and thermal stability, so that is quite advantageous to use carbon nanotube. So, basically people now are trying to develop this structured nanotube. So, this is a nano ordered carbon nanotube, they call it CNT forest, and that use the current collectors. Similar to the current collectors also, you can use this nanostructured carbonaceous material. I will describe about it in the last lecture of this module. And you can do the fine tuning by changing this growth. So, if you can change this distance depending on your solvated ions, you can make them inserted into this porous structure. So, that is advantageous. Now, pseudocapacitor, I will be having a whole lecture on pseudocapacitor, but let me just introduce it. Unlike the surface part, you see that it is a thin enough, I mean still it is a surface, but it is not like a battery, but there is a change of the redox, this electroactive material that is used along with your EDLC type of material. So, that certain pseudocapacitor which is not electronically conducting, you need to use a carbonaceous material to make a composite. So, there the idea is the first and reversible surface redox reaction takes place. It is not the adsorption of the counter ions on the charged surface, but there is a redox reaction is involved. So, that is the major difference, that the charge only present at the outermost surface of the conductive electrodes in EDLC, but it is present across the whole thin film region. So, if you have a thicker material, then do not expect that whole of it the redox reaction will take place, then it will be a battery, but at the surface of a thin film as well as most part of the bulk, you get this kind of intrusion, and that results this change in the redox in the active material. So, once it is something like this, then suddenly much higher pseudocapacitance, specific capacitance of pseudocapacitor is much higher, about 300 to 1000 farad per gram, and once you compare it with EDLC, it is only 100 to 250 farad per gram. So, that is why you are getting this advantage. So, there are various types of pseudocapacitative material that I will be explaining, and it is important for you to identify that what part is so called diffusion controlled and what part is actually adherence of the surface charge. So, that there are techniques to do that. In fact, I covered this in earlier part of the lecture, but as a recapitulation again I will show you that in the next lecture. So, metal oxide is used, RuO2 is already conducting. So, you do not need to add any conductive additives in RuO2, but oxide like manganese oxide or other transition metal oxide they are used. So, this is one type of material. Electronically conducting polymer, I already talked about it. So, ECP, they are also the candidates, particularly PANI and PPY and polythiophane, and also its derivatives, they are used as the pseudocapacitative material. So, the study material is the book Electrochemical Energy, Advanced Material, and this is your study material, and along with that there are excellent books by Conway and by Zhang. So, you can have a look, they are entirely on the supercapacitors, supercapacitative material. So, these books are there, and this book, this overview you can download from the internet, and these are the good materials to have a in-depth idea. So, in this particular lecture we talked about the classification of the supercapacitor. We made it only EDLC type and the pseudocapacitor type, but we can also expand this kind of classification, and mostly we concentrated the discussion on EDLC type supercapacitor and how the performance of a EDLC you can estimate from cyclic voltammetry, then galvanostatic charge discharge or electrochemical impedance spectroscopy measurement, what information you get. Then I provided some idea. Then we talked about certain EDLC material, mostly how activated carbons are made, carbon nanotube in different form, in a structured form or in a noodles type form, which can also be used as a current collector itself. You can use this material and other carbonaceous material like templated growth, controlling the porous structure that we introduced, and then we just define what are pseudocapacitative material, and we will continue it in the next lecture. Thank you for your attention.